Some people like to talk about AI like it's magic, but of course we know under the hood it's linear algebra, optimization.
They really complement simulations. So it's used as a tool for gaining fast insights into designs.
PhysicsAI is a product that we launched last year, and at the end of the day, it's for making fast physics predictions. The way it does that is by training deep learning models on historical simulations.
It's not feasible to run hundreds or thousands of design changes as part of an optimization, but with predictive models and geometric deep learning, this suddenly becomes feasible.
If you allow us to dream for a bit, I think there's so much potential synergy between AI and simulation.
All right, ladies and gentlemen, welcome to a new podcast episode today about Altair's PhysicsAI, and I'm very, very excited to have two specialists in my show today, Eamon and Jonathan. Welcome to the show.
Thanks, Jousef. Excited to be here.
Yeah, thank you.
I think before we jump into the topic of geometric deep learning, like the nitty-gritty of it, can you give us an introduction to yourself? Maybe Jonathan, you go first, and then Eamon.
Sure. Yeah. Hi. My name is Jonathan. I'm from Sweden originally. I've lived in London for the past 12 years. I did my undergrad and master's in Sweden at Lund University. My undergrad was in civil engineering and my master's in computational mechanics. And then I did my PhD here at the University of London, so Queen Mary University of London, at the Department of Aerospace, focusing on optimization algorithms and predictive modeling in the context of multidisciplinary optimization. I've spent the last 14 years working at Altair. First half as a CAE consultant, designing products using simulation and structural optimization together with our customers. And then I transitioned into software development, working in a team at Altair called Engineering Data Science Team. We focus on bringing AI and machine learning into engineering products. And I'm currently a development manager for Altair's geometric deep learning software, PhysicsAI.
Good, nice. Eamon?
Hi, my name's Eamon. I'm from Michigan. I study mechanical engineering at the University of Michigan. And 8 years ago, I started at Altair as an application engineer. So I was teaching meshing and structural finite element to a lot of the automotive companies in Metro Detroit. I got pretty interested in deep learning. I ended up doing a master's in computational science at MIT, where I focused on geometric deep learning specifically. I came back to Altair, and now I'm based in Boston, and I'm the data science manager for PhysicsAI.
Okay, thank you so much for the introduction, guys. So maybe let's define, we talked about PhysicsAI in the beginning. Maybe you could quickly give a short elevator pitch. What is PhysicsAI in the first place? And what is the benefit for engineers or your customers using it on a day-to-day basis?
Yeah, so PhysicsAI is a product that we launched last year. And at the end of the day, it's for making fast physics predictions. The way it does that is by training deep learning models on historical simulations. So let me back up for a sec. Probably a lot of your listeners know that engineering simulation has transformed how we build things over the past 2 decades. So we're able to simulate, whether things will bend or break, how fluid flows around an airplane wing, how our parts will be manufactured. And all of this has allowed us to design faster and do less physical testing. So engineering simulation is great. But the problem is, even these simulations can actually be quite slow. So for example, if you want to simulate a full vehicle car crash, that can take 24 hours, which means that if you make a design change, you have to wait 24 hours to see if that change was effective. And then you do it again and again. So PhysicsAI is part of this new horizon where we're using AI to augment the CAE process. What we do is we train PhysicsAI models on historic simulations. So these could be simulations from previous years or makes or models. And under the hood, PhysicsAI is using geometric deep learning to learn the relationship between the geometry of your parts, materials, boundary conditions, etc., and the physical response. And once you've done that, you can make lightning fast predictions on the order of seconds. And that resulting PhysicsAI model, you can kind of think of it as like a mini solver just for your application. So that's physics AI in a nutshell.
That's super interesting, Eamon. I would like to know more about geometric deep learning specifically, especially from the fundamentals, and how does it differ from the traditional AI approaches like classical deep learning, machine learning? Maybe Jonathan, you can talk a little bit more about that.
Sure, Jousef. Yeah. So I would say the goal of both traditional approaches and geometric deep learning is to predict the result of new designs using existing simulation data in order to make quick decisions. The main difference is the applicability and the lifespan of the model. So for traditional machine learning approaches, let's take a cantilever beam as an example. So you would start by generating data. So you would need to establish a parameterization. And so for the cantilever beam, say a width and a height of the section, and then you would run a number of simulations conforming to this parameterization. So in other words, a design of experiments. Then you would measure some responses that you're interested in. So for instance, scalar responses like a tip displacement or a maximum stress. And then you can train a model to predict these responses as a function of your parameterization. Then this model can be used for real-time predictions. So for things like what-if studies or optimization. The problem is that these models are only applicable to a specific parameterization. If you move away from this parameterization, you need to regenerate them. So for the cantilever beam example, if you add something like if you add a radius, for instance, the model wouldn't be applicable. You would have to collect new data conforming to the updated parameterization and then generate a new predictive model. In contrast, geometric deep learning doesn't require an explicit parameterization. The shape itself is the parameterization, which means that it can be trained on data from different sources. So DOEs with different parameterization, or even one-off designs that you've simulated as part of your project. And this allows the model to evolve with the design. And as you run more simulations, you can even update the model so that the lifespan increases even more. This is called transfer learning. So yeah, the main difference is applicability and the lifespan of the model. These models are really applicable during whole projects or even across projects.
That's super interesting. Yeah. With a background in FEA and CFD, I would be particularly interested in how you can use then or leverage geometric deep learning for these specific applications like CFD and FEA. I think the audience also would love to hear about that a little bit more.
Yeah. Maybe let me expand on something Jonathan said. He said the shape is the parameterization. So from a deep learning perspective, we've had good deep learning architectures for images, video, audio, tabular data for at least a decade. But if you think about it, what all of those data structures have in common is they're highly structured. If you imagine the pixels in an image, they form neat rows and columns. But as engineers, we're working with airplane wings and engine manifolds, and it's quite difficult actually to pose geometry in that structured way. It's kind of innately unstructured. And so geometric deep learning has given us the tools to apply the power of deep learning to this unstructured or non-Euclidean data. And the way that PhysicsAI is using that is by learning relationships in a data-driven way between geometry and physics. So that means that your parts can have different topologies, different meshes, boundary conditions, loads, thicknesses, you name it. And PhysicsAI is going to learn those relationships between the design and the final physical result. And so really under the hood, that's how PhysicsAI is able to make a shortcut, if you will, and deliver predictions that are so much faster than a traditional solver.
Mm-hmm. I would be interested in the efficiency and the accuracy of using AI to enhance simulation. Maybe we can talk a little bit about the, maybe let's call it challenges that these technology address for both domains.
Yeah, so I think a common misconception is that these methods are improving simulation qualities or that they replace simulations. I'd say that they really complement simulations. So it's used as a tool for gaining fast insight into new designs. For instance, let's take crash and aerodynamics as examples. Both of these disciplines require really long running simulations. It can take, for instance, it can take 24 hours to evaluate how effective a design change is in both of these fields. And engineers, they use their experience to screen ideas, and then only simulate a few candidates that they think are good ideas because of the simulations being taking so long. So geometric deep learning can really be used as an additional tool to complement your experience in getting immediate answers to multiple design iterations in a day, right? And similarly, designers can use this tool to assess and to screen designs before they send their designs to the CA department. And finally, also, this enables optimization for these disciplines. For instance, for some disciplines like the two I just mentioned, it's not feasible to run hundreds or thousands of design changes as part of an optimization. But with predictive models and geometric deep learning, this suddenly becomes feasible.
Mm-hmm. I mean, we engineers, we're usually very skeptical, never change a running system. If something works, it works. And now the question is like, how can I even trust these geometric deep learning models? And if so, how can we check that?
Yeah, it's a great question. How do we trust these models? So first of all, in all deep learning, there's a best practice of testing your model after it's been trained on designs that it's never seen before. This is crucial because here we're proving that the deep learning model has actually learned the correct relationships between shape and physics, not just memorized the training data. And actually, CAE analysts are used to doing something quite similar in a solver benchmark when they're assessing the accuracy of a solver. Here it's really the same thing, but we're assessing the numerical accuracy of the model you just trained. Now, these PhysicsAI models, if you train them on a car, you wouldn't expect good results if you suddenly tried to make a prediction on an airplane. I think as engineers, we have a notion of, interpolation is safe with data-driven methods, extrapolation isn't. But now, without any explicit parametrization, how do you know what's safe and what's not? If you ask an LLM a question it doesn't know the answer to, it just makes something up, hallucinates. But we want to be much more conservative. So we spend a lot of time thinking about this, and we've invented something called the similarity score, and it tries to tell you how applicable this trained deep learning model is to this particular input. Under the hood, we're doing something called novelty detection in the machine learning world. We're trying to quantify how similar is this new input you're about to give to what the PhysicsAI model has seen in the past. And so the similarity score is just another layer of confidence that we give to our users, that they can trust the model they're using. And then the last thing I want to say on trust is we never use PhysicsAI models for final validation. These are fast estimates. They allow you to evaluate far more designs than you could have normally. And then once you've found that best design, you're always going to run the FEA, the CFD one final time to verify that the design is as good as you think it is.
Yeah, that makes sense. I'm wondering, we talked a little bit about it, like the benefits of using AI in your workflow, in your engineering workflow. I mean, from an optimization or optimizing the workflow perspective, how does it affect the engineer's work on a day-to-day basis? And I think one thing we have to really point out is how it affects the engineer itself, because the engineer is a trained engineer on that specific domain that he's a specialist in, and he doesn't need to be a machine learning expert or data scientist using your tool. I think that's super cool. Maybe you can talk a little bit about that.
Yeah, that's a great question, Jousef. As we pointed out, geometric deep learning really has the potential to transform how engineers work with simulation. But you're right, to be transformative, it really needs to be accessible. So we want it to be available to every CE engineer and designer. So we decided to make it available in Hypermesh initially, which is our flagship CA platform. And that really makes it available to a huge number of engineers. But it shouldn't just be available, it should also be easy to use. So you shouldn't have to be a data scientist, as you pointed out, but also you shouldn't have to be a programmer, and you also shouldn't have to know the intricacies of a solver. So you shouldn't have to be a solver expert. And CAE data can be really complex. So you have solvers with different output files and data formats. You have element types, different element types like 1D, 2D, and 3D. First order, second order elements, different numbers of layers for elements. You have results at centroids, at Gauss points. You have scalar, vector, tensor types. You have different materials, different properties. Shells have thicknesses, solids don't. We have linear and nonlinear analysis. We have static and transient analysis. There's so much change, so much complexity in CA data. And it's really not straightforward to transform that data into a format that is suitable for geometric deep learning. So it was really important for us to make this into a no-code workflow and directly integrate it into our software. So in PhysicsAI, in Hypermesh, all you have to do is select the simulation files that you want to train based on, which data types you want this model to be able to predict, and we handle the rest for you. Secondly, another thing that I find is really important for accessibility is collaboration. So I talked before about that these models are more applicable, have longer lifespan. This also means that you're probably not going to be the only one using this model. You want to make it available to your colleagues. And for that, we use our cloud platform, Altair One, which enables collaboration, and it gives you also access to scalable compute. PhysicsAI is heavily accelerated on GPUs, so that's important. And not only that, but we also connect to this platform from our desktop product. So you have the ability to submit trainings from the desktop products. You have the ability to discover models that your colleagues have shared with you directly from the desktop product. So yeah, in summary, making PhysicsAI accessible to engineers and designers is really important to us.
Mm-hmm. Yeah, thanks for the insights. I'm wondering, can you talk about specific use cases when it comes to FEA and CFD simulations? Because I have to point out one thing. I've seen a lot of AI companies that pretend they can solve specific use cases, but they never showed it. And I think for Altair, when you look on the website, you have some specific use cases that you've already solved, which I think is a huge benefit. So you already have proven that this works. So maybe you can walk us through some examples that you've worked on in the past.
Sure. Yeah, there are a lot of use cases, but our vision is to support all solvers in all physics. So maybe I'll just go through some examples. We have one customer right now. They are automotive crash experts. And crash is a notoriously difficult design problem. The relationships between shape and physics are highly nonlinear. There's these knife edge conditions, parts crashing into each other and failing. So they are designing a crash box, and they've been able to take these 14-hour finite element simulations and down to like a 10-second physics prediction. So it's just been transformative for them because they're able to explore so many more designs in the same amount of time than they could with FEA. I saw another crash PhysicsAI example recently where the data that was being trained on would have taken like 15 CPU years to simulate. But PhysicsAI trains on it just overnight, and then each prediction is like 4 seconds. So we're really talking about orders of magnitude speed up. So that's crash. PhysicsAI is used in other structural domains. So durability, we support linear and nonlinear, structural FEA, NVH, like modal analysis, random vibration. We're used a lot in CFD. So internal flow, like an engine manifold or an HVAC system, and external aerodynamics. So if you want to know the drag coefficient for a new vehicle, for example. PhysicsAI is also being used for manufacturing simulations. So if you want to predict the warpage that will occur when you injection mold a part, you can do that with PhysicsAI. It's being used with casting simulation and with the forming of sheet metal. PhysicsAI is being used in electromagnetics, so completely different physics, but same tool. If you want to know the torque that your electric motor will produce, you can do this with PhysicsAI. And in antenna design, the far field pattern of an antenna can be predicted. People are using PhysicsAI not just with simulation data, but also with physical test data. So because PhysicsAI can output a contour, a curve, or a scalar value, you can measure relationships in measurement values in the field and then learn a relationship between geometry and those measurements. And maybe the last thing I'll say is sometimes it's not about saving simulation time, but saving model build time. So as many of your listeners probably know, it can take a lot of manual time to import geometry, clean up the geometry, mid-surface, a mesh, apply boundary conditions, materials. All that manual time to get the simulation set up sometimes is more than it actually takes to compute. And with PhysicsAI, we don't have those strict mesh quality criteria that classical techniques have. In fact, sometimes we're even making predictions directly on the CAD itself. And what that means is, like, we had one customer where their simulation was maybe only a few minutes, but the whole process of setting up the simulation would take an hour. And again, with PhysicsAI, that just goes to a few seconds.
Yeah. Let's talk about other innovations that you guys have developed using geometric deep learning. I know innovative is like a very uninnovative term, but maybe you can talk about other innovations that you guys have worked on or maybe will be working on in the near future or far future.
Sure. So I think one of our big innovations, like Jonathan said, is just bringing geometric deep learning into a CAE environment. Where you don't have to be, a PhD in deep learning in order to train massively powerful models. But maybe I can touch on some of the other innovations more on the algorithmic side. So we have one architecture that's based on a graph neural network. Some of your listeners will be familiar with graph neural networks, so they're quite expressive and quite general. A lot of the vanilla graph neural networks were designed for things like social networks or molecules. And if you take those vanilla neural networks and apply them to simulation data, they tend to not work so well. And so one of our big innovations is a proprietary graph neural network architecture that we find works really well across a wide range of simulation physics. We have another architecture. That one's actually based not on a graph neural network, but on a transformer. So you've seen transformers be revolutionary in natural language processing and computer vision. We now also have our own transformer architecture, which is proprietary. And we're finding that one is particularly well suited for these CAD-based predictions. Both of our architectures, we've enabled transfer learning. So the idea of transfer learning is you can take a trained PhysicsAI model and you can adapt it or update it to a new task with way less data than you would have needed to train from scratch. It's a bit like if you've learned one musical instrument, it's now easier to learn other musical instruments. So if a PhysicsAI model has been trained on, let's say, one crash problem, and now maybe I have a limited amount of data, maybe for the current year, the current design cycle, I can take that trained model and use transfer learning to update it with new data. And now I have a model that is able to generalize to this new cycle far better than if you had tried to train from scratch. So I think because we're in a data scarce domain, transfer learning is going to be really impactful. Maybe the last innovation, I've touched on it already, but this idea of a similarity score. We want to be innately conservative about our predictions as engineers and that really manifests itself in quantifying when the model is applicable and when it's not. So maybe those are some of the innovations that we're most proud of.
I talked a little bit about the status quo. What have you guys planned for the next few years? Maybe some sneak peek in this podcast. What's coming?
Sure, yeah. So PhysicsAI was released at the beginning of last year, and we've seen really fast adoption amongst our customers. And at the same pace, the team has grown. We're moving really fast. We're working really hard on improving both the technology and the UX. So yeah, I can touch upon a few major topics that we're working on right now. And the first one is data curation. So that includes extraction, visualization, and cleaning. It's important to understand that deep learning models are only as good as the data that we train them on. A lot of people think that the way to improve deep learning models is by tweaking the neural network parameters or settings. We know that the best way of obtaining good deep learning models is by having good quality input data. So it's really important for us to streamline the process and make it more transparent, especially allowing users to act on data quality issues. This really is key for maximizing model quality. So this is something that we are continuously improving. And secondly, we're working on continued integration. So I mentioned before that we've made it available in HyperMesh, but it really should be available in the environment that you are used to, the environment that you are using daily. So we are shortly adding it in HyperMesh CFD, which is our end-to-end CFD solution. We're adding it into Inspire, which is used for early stage product design. And we're also adding it into SimLab, which is our multi-physics platform, which includes solutions for electronics. And also we are improving our cloud workflows. I touched before about on Altair 1, which gives you access to scalable compute. GPUs are important for PhysicsAI as it's heavily accelerated. It enables collaboration, and I also mentioned how it's seamlessly connected to our desktop apps. So this will continue improving those connections between the cloud and the desktop apps, and will also enable using PhysicsAI in a web app. So this gives you the flexibility to curate data, train, manage, and operationalize your models directly in the web browser. And finally, Eamon mentioned algorithm development. Of course, this is a big topic for us. Eamon mentioned the transformer that will be released shortly, and we'll continue improving accuracy, speed, and trust in our models through continued innovation. Yeah.
You got me all super excited. So I have to talk to you after the podcast to get my hands on PhysicsAI. I think for the more techie and nerdy people listening to this podcast, right, they want to maybe learn a little bit more about the technical aspects of it. So how does PhysicsAI actually use GNN, so graph neural networks, for accelerated physics predictions?
Yeah, so that's a great question. So how can a neural network with no prior knowledge of geometry or physics learn the relationships between, for instance, a car and its drag? And yeah, this is really thanks to deep learning methods providing the ability to extract information from low-level details. So, for instance, convolutional neural networks can learn from pixels in an image. Similarly, GCNNs or graph neural networks can learn from positions of nodes in a mesh. And the input that you feed to PhysicsAI is really the same that you would give to a solver. So you provide it the shape, so that would mean its coordinates and connectivity, as well as anything else that define the problem. So boundary conditions like loads, constraints, materials, anything. This really depends on the scope of your model, of your model, what it should be applicable to. And you can imagine that this type of parameterization can have very large variations. So the expressibility of this model, it really needs to match the potential design changes that the model can be used for. And so this often leads to millions of parameters. So in neural network speak, these are called weights. We randomly initialize those weights, and then you feed existing simulation data, training data, through your neural network. And since these weights are randomly initialized, the first thing you get is a guess. And this guess is certainly wrong to begin with. And we quantify this guess using an error metric. So this is called a loss. And because the neural network is differentiable, not only does it know the loss, but it also knows the gradients of the loss with respect to the weights. And so you can use optimization to minimize this loss. So this really is what training is. It's setting the weights such that the loss is minimized, meaning that the model captures trends in the data, or in other words, learning relationships between shape and physics.
Yeah, that's super insightful. I'm thinking more into the future, right? We talked about FEA, CFD, electronics, simulations. What else is potentially possible if we think about physics AI and any other type of simulation, for example? Do you guys have a vision?
Yeah, well, if you allow us to dream for a bit, I think there's so much potential synergy between AI and simulation. Some people like to think of AI as magic, but under the hood, it's linear algebra, it's optimization. It's a lot of the same numerical tools that are in the simulation world. For that reason, I think there's a lot of ways they can be fit together. So, for example, you could use deep learning as a preconditioner or as generating a good initial guess, which is then refined by the solver. You can go the other way too. You could run a low fidelity simulation, maybe on a coarse mesh, and have it refined by deep learning. People call that super resolution. You could also simulate a few time steps with the solver and have the deep learning model take over from there. And then, there's this whole history of optimization techniques that make use of multi-fidelity, when to use a fast approximation and when to use a high fidelity accurate result. And that, to me, seems very much applicable to this new AI realm as well. And then, we're seeing the ability of deep learning models not just to predict physics, but actually synthesize 3D shapes themselves. And so you can imagine one day deep learning models actually generating the design for you. And these Gen AI models, if you think about what generation is, it's really just learning the distribution. In a sense, it's kind of like building a design space, the way an engineer would construct a design space, only it's happening in a data-driven way. So I can imagine deep learning models generating our engineering designs. Of course, we're not just trying to generate a design. We want to generate a design that's performant and manufacturable and novel. But I think that's an exciting direction. And then, in computer vision and natural language processing, foundation models have been so transformative. The way we've gotten to these foundation models is through massive scale and self-supervision and some algorithmic improvements. And, you have to wonder whether the world of CAE will follow a similar direction. Of course, we have some unique challenges, right? Like our data is intellectual property, so it's really hard to, you're not going to scrape the web for every, modern car design, for example. But you have to wonder whether some similar directions will apply to our field. So in conclusion, I'm just really excited about what the future holds.
That's super exciting. Yeah, I'm also super excited, and I think the listeners will be as well. I think people should actually just check it out. We'll put all relevant resources in the description so people can read white papers, watch demos, etc. Any closing remarks from you guys? Anything you want to let the audience know? Any tips, hints?
I just want to say that I agree that there's a lot to be excited about. I really love that we're able to provide this technology to engineers and designers. I'm really confident that this will transform how CE engineers and designers work. And I think that we've only scratched the surface so far in terms of use cases. And we'll continue to innovate and work with our customers to bring advanced deep learning technology into their day-to-day job.
Sounds exciting. Looking forward to hearing more from you. Maybe we'll even have a second part in the future. Let's see. Eamon and Jonathan, thank you so much.
Thanks, Jousef.
Thanks so much,
This was
Jousef.
fun.
It's been fun, yeah.